Understanding physics, hard bits, and this video is about simple harmonic motion, particularly talking about the equations that you need to know. Simple harmonic motion equations. So what is simple harmonic motion? Well, this isn't a definition of SHM, it's just a description. So an object oscillating about a fixed point. For example, this mass on the end of the spring, the mass is oscillating, and you'll see looking at the graph, there's the center of oscillation, and the center of oscillation, you can also call it the equilibrium position. If the mass wasn't moving, it would be in equilibrium, and the displacement, if you like, would be zero at that particular level. But it's bouncing up and down, it's oscillating about that point. So its displacement is negative, and then it's positive, and then it's negative, and then it's positive. And displacement against time is sinusoidal. This is for SHM, undamped sinusoidal SHM, perfect SHM, if you like. Again, this is not a definition, this is just a description. We'll talk about the definition in a bit. So, displacement against time is sinusoidal. Here I've done it as a cosine, against time. The maximum displacement is the amplitude, capital A. The time for one oscillation is the period, which is capital T. Always look at the labels. This is against time, yes, so the period, capital T, horizontally. Now we can express it, the equation for this curve, x equals a cos omega t. This is, if you like, if you lift up the mass and then let go, and when you let go you start the stopwatch, then you'll get a cosine. The difference between a sine and a cosine is just where you start from. In fact, AQA, it's cos omega t. On OCR, it's sine omega t. It doesn't matter. It's the same thing. It is sinusoidal. But for AQA, we say x equals a cos omega t. A is the amplitude. X is the displacement. T is time. What's omega? What's omega then? Well, omega is a constant related to the frequency. It's not the angular velocity. Now, I know that these equations, they're the same equations that you use in circular motion. And in circular motion, omega is the angular velocity. Here, don't think of it as the angular velocity. It is just a constant. Omega is a constant which is related to the frequency. Omega equals 2 pi f, or 2 pi over t. Yeah, a constant related to the frequency. There will be physics teachers going blue in the face saying, oh, it's actually the angular velocity of the auxiliary circle. And I would say, let's not confuse things. It's just a constant related to the frequency, and it is measured in radians per second, just as angular velocity is. Make sure, by the way, when you do these sums with cos omega t and all, that you're in radian mode on your calculator. And don't forget to put it back to degrees after you've done this question. So there are three quantities that we're interested in: displacement and velocity and acceleration. How do they vary with time? How do we calculate them at any point in time? And how are they related mathematically and graphically? How are they related? So that's what I'm going to be talking about. Displacement, x equals a cos omega t. Yeah, we know that it's a cosine in AQA. X is displacement, a is amplitude, omega is a constant related to the frequency. Now, velocity, you should know, because you do A-level maths, if you differentiate x, so dx dt gives you the velocity. And I'm sure you've done differentiating trig functions, haven't you? So if you differentiate cos, you get minus sine, and you get another omega, an extra omega. So V is minus A omega sine omega t. There is another expression for velocity. This V is plus or minus omega times the square root of A squared minus X squared. I'm not going to talk about where that comes from. If you look at it, you can see there's probably a bit of Pythagoras going on there. Yeah, you know, x squared plus y squared equals r squared, whatever. But this is an equation that at AQA you need to know to work out the velocity. Bit more about that later. Now, if you differentiate x, you get velocity. If you differentiate v, you get acceleration. So if we differentiate this term again, if we differentiate sine, we get cos, and we get another omega comes out, so we get A equals minus A omega squared cos omega t. But what we can do now is we can substitute for A cos omega t, because A cos omega t is equal to x. So if we sub for A cos omega t, that becomes this. Nice and simple. A equals minus omega squared times x. Remember that omega is a constant, so A equals minus a constant times x. A is proportional to minus x. A few other things to mention here. Now, those are the equations that you need to know. Those are the ones that you definitely should make an effort to learn. Those are the ones on the formula sheet. They are the equations you need to know. Not the V is minus A omega sine omega t. You don't need to know that. You do need to know that V is a sine function. Yeah. Looking at this equation here, now one thing we can deduce from this, the maximum velocity. Now V max will be when that is equal to 0, isn't it? So when that term equals 0, then it's just the square root of A squared. So V max is, well, V max is plus or minus omega A. The maximum speed would be just omega A. That's important, remember that. Yes, comes up on many a multi-choice. V max is omega A, and that's when x equals 0. When x is equal to the amplitude, then the velocity is 0. So if x squared was a squared, then a squared minus a squared is 0, so v is 0. Another equation it mentions on your specification is a max, and a max will just be when x is a maximum. So when x is equal to the amplitude, so the maximum acceleration is minus omega squared times the amplitude. Very mathematical, I know, but there you go. Okay. When you do physics at higher and higher levels, it's the difference between physics and mathematics tends to fade away. Graphically, now let's discuss this graphically. X equals a cos omega t. So there you go. There's x, and there it is, a cosine function. Now, velocity. If you've got a displacement time graph, then you should know that the gradient is the velocity, isn't it? So the velocity, now what's the gradient there? Well, the gradient there is 0. So the velocity at that point in time is 0. The gradient there is a negative maximum. The gradient there is 0. The gradient there is a positive maximum. The gradient there is 0. So what would a graph of velocity against time look like? And there you go. Just as I said, the gradient there is 0, so the velocity is 0. The gradient there is a negative maximum, so there's the velocity, etc. So just by looking at the gradient of the displacement time graph, we can figure out that the velocity time graph is a negative sine function, a minus sine function, as we stated before. So that's displacement and velocity. Now, what about acceleration? Well, you remember, don't you, that the gradient of a velocity time graph tells you the acceleration. So this is our velocity time graph, the purple one. So acceleration there is a negative maximum. Acceleration there is 0. Acceleration there is a positive maximum. Acceleration there is 0, etc. And the graph is like that. Okay. Again, looking at the purple one, a negative maximum, yeah, so it's there. Here the acceleration is 0, yeah, so it's there. The green line is my acceleration. Here it's a positive maximum, so the acceleration is a positive maximum. Okay, and look, there it is. A equals minus a negative cosine function. Okay, be able to sketch this. What you say? Well, you know, if you've got it in an exam, then basically draw your axes, do some construction lines, yeah, some construction lines, and then you can do the, again, remember x is a cosine, velocity is a negative sine, and then acceleration is a negative cosine. You should be able to sketch this. I know it looks like a nightmare, but have a couple of goes at it, you'll get used to it. Let's finish with this now. The red one is my displacement. Yes, the green one is my acceleration. Just looking at the graphs, what's the relationship between them? X is a cosine, acceleration is a negative cosine. They are the opposite of each other. Yes, so if one's positive, the other's negative, vice versa. Yes, they are the opposite of each other, and that agrees with this equation here. A equals minus omega squared times x. Yeah, they are not inversely proportional to each other, they are proportional to each other with a negative constant. Yeah, so acceleration and displacement are proportional to each other, but we say in the opposite direction. And so we get to our definition. This is our definition of SHM, which you should learn. An object is executing SHM if its acceleration is proportional to its displacement from a fixed point and is always directed towards it. Yes, in other words, acceleration and displacement are proportional to each other, but in opposite directions, which is the negative sign. Now, there are two examples that SHM that we need to be familiar with, okay? And that's the mass on a spring and the pendulum. Now, in real life, there's lots and lots of things which oscillate. Looking at these pictures here, so you've got this kind of grandfather clock and the pendulum. You've got a pendulum in a grandfather clock. Hopefully you've seen the video of the Tacoma Narrows Bridge. If you haven't, make sure you look it up. And that's oscillating. That can be modelled. It's called a torsional oscillation, but it's basically a mass on a spring. Walking. When you walk, your legs do something called an inverted pendulum, an upside down pendulum. You can model walking on pendulums. The jackhammer there is obviously mass on a spring. Molecules vibrate, like when you put water in a microwave, the molecules oscillate, and that's masses on springs. These are all oscillating systems, and we can model them, we can simplify them by saying, well, it's just a mass on a spring, or it's a pendulum. Okay, well, I used to have an old car, and when I drove the car, at certain speeds, the wing mirror would wobble like mad. It was a mass on a spring. A skyscraper in an earthquake, you can model that as either a mass on a spring or a pendulum. Now, mass on a spring. Let's consider this. First diagram, a mass is in equilibrium. So this is our equilibrium position, our center of oscillation. Mass M, the effective stiffness of the springs is K. If we displace it, if we grabbed hold of imagine it's like a trolley and you pulled it that way and you gave it a negative displacement, the restoring force is in the opposite direction, so the acceleration will be in the opposite direction. So F equals minus Kx. So F equals ma, F equals minus Kx, ma equals minus Kx, A equals minus K over M times X. Now, A is minus omega squared X, therefore omega squared is K over M. T is 2 pi over omega, therefore T equals 2 pi root M over K. So basically what I've just done is I've just derived that equation, which you definitely need. T is 2 pi root M over K. Do you need to know this derivation? What you must appreciate is that the displacement and the acceleration are in opposite directions and proportional to each other. Okay, and that's where this equation comes from. The pendulum. Okay, so we have a string of length L. So there's your length of string L there. It's got a bob on the end. We say it's a light, inextensible string. Doesn't stretch. Yeah. Ignore the mass of the string as well. And we displace it horizontally a distance x, so there's a restoring force in the opposite direction again, so the acceleration and the displacement are in opposite directions and proportional to each other. Here's the maths, the restoring force. Now the restoring force is going to be the horizontal component of the tension. So the tension in the string is T. This angle here is theta, yeah, so it's F is T sine theta, and sine theta is X over L. Looking at this triangle here, there's X, there's L, so sine theta is X over L. If the angle theta is small, then T is equal to mg, yeah, the tension is just mg. If the angle is small, etc., etc., A equals F over M, equals blah 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 G over L times X. Now as A is minus omega squared X, omega squared is G over L, T is 2 pi over omega, so there you go. Okay, again, will you be asked to derive that equation? No, but there's a few important points here. First of all, again, the acceleration will be in the opposite direction to and proportional to the displacement, and in AQA they make a point of this. There is a small angle approximation, which is why for a pendulum you can only use that equation if the oscillations are small. You know, I do experiments with a class, and we do like an experiment with a pendulum, and basically if there's your pendulum, the bob of the pendulum should be like small oscillations, okay, not whoosh whoosh massive oscillations. Why? Because then that equation doesn't work. Why? Because in the derivation there is a small angle approximation. Yes, we assume that theta is a very small angle. You might get, like I said, mass on a spring or pendulum. You could get another one. This one on the left here is a liquid, and we call it a U-tube. Not the YouTube you're watching now, but a tube in the shape of the letter U. And this liquid is sloshing up and down. Another one is what we call a torsional pendulum. Okay, you might remember the Cavendish experiment to get a value of big G. That involved a torsional pendulum as well. If it's another SHM like that, you'll be given all of the information that you need. For all of these SHMs, it's T equals 2 pi root something over something. Yeah, something divided by something. It's what those somethings are, then you'll be given, you'll be told. It may be the moment of inertia. If you do your engineering physics, you'll know what I'm talking about. In fact, I think for the torsional pendulum, I think it's I over C, where C is the torque per unit angular displacement. Ignore me, you don't need to know. Move on, next slide quickly. Right, a couple of questions for you to have a go at. Yes, practice using these equations. So read this, do the sums, get it done. Pen, paper, calculator. The answers are in 3, 2, 1. There you go. Hopefully you agree with me. Yeah, work out the period. T is 2 pi root m over k. For the maximum kinetic energy, so half m v squared, using the maximum velocity, so you need to work out omega first. Interesting here, if you do a half kx squared, which is the energy stored in the springs, yeah, you get the same answer, which is, well, not surprising really. And then the speed of the trolley for a particular displacement is using that a squared minus x squared thingamajig. Here's a couple more questions for you to do. Pendulum questions. Big pendulum. 28 kilogram bob, 67 meter long wire. It's built by a guy called Foucault. Look it up. It was used to demonstrate the rotation of the Earth. Not really interested in that at the moment. Just big pendulum. Pen, paper, calculator. Do the sums, and the answers are in 3, 2, 1. There you go.